happens. So, shoot, totally going to look up how these things are supposed to be named, and then we could talk about it again. We'll go through and deal with epoxides today. Epoxides probably thiols, so we'll finish chapter 14. We're then going to double back and take a look at conjugated dienes. I'd hope to do a little bit more work on figuring out what chapter that was first off. There's some more slides that I wanted to add into it as well. So hopefully I'll just finish this stuff and I won't have to worry about missing that information. That information has also not been posted to Canvas yet. So I'll get that up as soon as our after class. Okay, so yes?
On Canvas, I know last week you said you were going to add on a couple things for the alcohols that were missing off the...
That's right. I have not gotten to that yet. I'm going to have to go back through and get those added in. You can send me an email to remind me. That's the best way to actually get me to do something because I'll actually have it on paper. Other questions? Okay, so hopefully the plan for this week is to finish up our epoxides, do a little bit of the conjugated diene stuff, kind of very, very superficial, and hopefully then have some time left over to answer questions and get you kind of ready for the exam on next Monday. Okay. So with epoxides, I said I was going to look up the nomenclature on it. I didn't, so I can't give you any more information than we had last week. Okay. Did anybody happen to look up already epoxide nomenclature? Can share with the class how to do it?
You had it right.
So the names I got were right, but are the directions right?
Oh, I didn't.
Yeah, I don't think my summary of directions was right. Pretty sure the names I came up with were correct. Should we go through and attempt to name these again? Okay, good. I didn't want to name them again. So now we can actually look at the chemistry for our epoxides. What we're looking at is, like we said already, a very stressed ring because those bond angles are shrinking down on the structure. So what we want to do is come up with ways to both make it, because it's synthetically useful, because it wants to pop open. We then also have that issue of it wants to pop open, meaning it's not going to be easy to make to begin with. So there's really two common methods that we can look at. It's a substitution method as well as an addition method. So those two main categories for our reactions. Any ideas what substrates we're going to be starting with? We're going to start with a substitution. Any idea what bond we might want to make if it was a substitution reaction? Why the carbon-oxygen, not the carbon-carbon? So we can pick either one of those. Okay, what we're looking for is, again, the most polar bonds. The most polar bond is going to be that carbon-oxygen. We've got a large partial negative on our oxygen and a large partial positive. Here's the true test. You can actually see the blue. Hey, it worked out. And that large partial positive on that carbon. So if we were going to say break that bond, what we'd want to do is work backwards and say, okay, let's break just that bond. Kind of leave the rest of this structure as it is. We got our oxygen now with all those lone pairs, with our negative, and our carbon with a positive. Okay. Highly, highly reactive. Why? All the charges. So if we're going to come up with some way to make this structure, we're going to come up with some way to simplify that or stabilize that at least temporarily before we can finalize into the epoxide. So how could we stabilize that oxygen? We could start with an alcohol. So our starting material could very easily have been an alcohol. How do we stabilize that positive carbon? It's a little bit trickier. We want something that's easily removable, and we want something that's going to make that carbon positive. What was that? We typically want to pick something like a halide. Other possibilities that get thrown out there. Remember, this is organic chemistry, so we can come up with, run through all our possible options. Hydrogen. Would hydrogen work to make that carbon very positive? No. If anything, it's going to make the carbon more negative. Why would it make it more negative? Carbon is more electronegative than hydrogen, so hydrogen's a bad option. We could try and put a metal on there. You don't even have to get specific with that. You just made it a metal. It's the issue with metals. Metals have an even lower electronegativity than hydrogen, meaning that carbon would become even more negative. Not what we want. We could then try and look at nitrogen, okay, or even another carbon. Another carbon is going to leave it neutral, so no easy exchange there. If we did a nitrogen, nitrogen's pretty electronegative. That could make that carbon positive. Problem with nitrogen? How many bonds can it have, or should it have? 3. We'd have to account for 2 more bonds. Those 2 more bonds could potentially react. Further with nitrogen, nitrogen has that lone pair. That lone pair is also potentially reactive. So nitrogen's not the best option because we've got a bunch of other chemistries that could occur at the same time. So we want to limit that. So we could move to more electronegative, go oxygen. Same issue with oxygen. You get that 1 extra bond. If we made it a diol, we have both those alcohols now potentially reacting, getting in the way of each other, kind of problematic. We want to pick something as simple as possible. What's nice with our halogens? No other bonds. They're a good leaving group. One of the reasons they're a good leaving group is because the electrons on there aren't particularly nucleophilic, okay? Because we already have that 1 bond that the halogens could have. So our halides typically are a good case for looking at a possible synthesis for the alcohols. Okay, so what we've done is kind of reverse engineered the individual pieces that we could put into this. The next one, that's a lot trickier in my opinion, would be the addition reactions. Trickier for multiple reasons. One, most of us are a bit weak with our addition reactions for any number of reasons you can come up with on your own. And they also aren't the easiest to see. If we're going to do an addition reaction, what are we starting with? We have to start with an alkene. Okay, why would an alkene be particularly reactive, or a good idea in this case? How many bonds need to be made when we react with our alkene? 2. If we take a look at our epoxide, how many bonds would we need to make? Or break to go in the reverse? 2. Which means we need both of those carbons to be potentially reactive. And this is where this one gets a little bit trickier, trying to decide positives and negatives on those. Well, if we made 1 positive, what should the other one be? Negative. Okay. Well, then that puts 2 negatives next to each other. So the reaction in this case, our addition reaction with the alkene and a particular reagent, that reagent is going to have to supply what? What atom is currently missing as we go from the alkene to our epoxide? Our reagent is going to have to somehow supply an oxygen. And based on the alkene, we do have positives and negatives. So that oxygen is going to have to come in from one angle, supplying electrons, and from the other angle, being able to accept electrons. So we get some kind of weird oxygen chemistry. Or oxygen weird, why not? Okay. Your standard reagent that you'll see pretty much everywhere is known as CPBA, which we'll look at here in just a little bit. Okay. Questions about our basic breakdowns on each of these pieces? Make sense so far? So, synthesis of our epoxide. Forget why I put the addition there. Hopefully it'll come up here in a second. Look at our substitution reaction. We're starting with our alcohol, and we picked an alkyl halide. In this case, the halide is bromide. Why bromide and not something, say, like fluoride? It's bigger, which means what? It's a better leaving group. Okay, so we picked bromide because it's nice and big. Good as a leaving group, potentially react better in this case. That's a pretty big typo. You'll notice the base that we use in this case is what? Is there a problem with using sodium hydroxide as a base? What's that? What do you mean? What is adding NaOH going to do to this? So NaOH brings in what? Sodium ion and hydroxide ion. Of those two, which one's reactive? So when you see NaOH, what you should be seeing is OH minus. What do you mean you already have an alcohol? What are you saying that OH can do?
Well, just says there's already an OH in what you're trying to add it to. But it would
I
attack.
think I see what you're saying. So why add an extra oxygen if we already have one there? Well, we might add the extra oxygen because that's reactive and allows this thing to go.
But it's not reactive. The OH wouldn't, like the OH wouldn't, the OH on the first, on the reactant wouldn't really grab the hydrogen from the NaOH. So
Our
I don't want that.
alcohol isn't particularly reactive to sodium hydroxide. Remember, we get that pretty crappy equilibrium reaction. So it's not the easiest one. That's not going to generate a good, strong nucleophile by removing that hydrogen. Okay? So we might want to use a stronger base to go in and remove the hydrogen. Why remove the hydrogen at all?
So that oxygen can make that second bond.
Why remove the hydrogen before we make the second bond?
Reactivate the alcohol.
It's not, our pre-activation is forcing it to act as a leaving group. Is oxygen a good nucleophile in this case, with it protonated?
No.
No. Okay, if we look at our standard substitution reactions, water's not an awesome nucleophile. It can act, but if we were going to classify a reaction based on the nucleophilic character, and we said water versus hydroxide, okay, hydroxide will act in which mechanism, SN1 or SN2? You guys are supposed to be strong with substitution. Come on now. SN2. Our SN2 pushes strong nucleophiles, negatively charged species. If we take a look at water, it's not a strong nucleophile because it doesn't have that negative charge. Okay? So if we're going to look at our reaction and trying to force this to occur, do we want a strong nucleophile? Is it something that we think could possibly happen without a strong nucleophile? Look at the product. Is that product a nice, easy thing to form? Everything's nice and happy with all its bond angles? Oh, we're looking at a very stressed product. So to force that product to occur, we're going to have to up the reactivity of our reactants to get that bond angle to crunch down. Okay? So our alcohol is not generally nucleophilic enough to close that gap and allow for the epoxide formation. So we need to make it a better nucleophile. Once it's a better nucleophile, it can now drop that bond angle down, or more easily drop the angle down. And once it's actually formed that carbon-oxygen bond, now it's locked in place. It's kind of stuck with what it's got. Okay? So there's another big issue with our hydroxide, though. And it was vaguely addressed here. Hydroxide can act as what? A base and nucleophile. Is there a partial positive carbon in here that could act as an electrophile? See right there. And it better act as an electrophile. Why? It's how we made the epoxide. Our electrons from our alcohol need to come down and form that. If we add hydroxide, we've got an issue. That species can act as a nucleophile, and instead of getting the epoxide, what do we get?
Two alcohols in it.
We end up with the diol. Is that what you were about to say as I talked over you?
Yes, indeed.
Yeah. Well, that's not what we want. We want the epoxide. So what we're going to need to do is add a base that can cause this to occur without acting as a nucleophile and crunching in there. So a good option, something like sodium hydride. Hydride is not a reasonable nucleophile. It's so small and reactive that it's going to react with the external features first, like our hydrogen, and be emitted off as hydrogen gas. So we would favor something more along the lines of sodium hydride to go through and do that for us. Okay? The hydroxide is a bit dangerous. Whoa, hey now. Okay. So yeah, that's a bit odd how I got that phrased. Okay. We could get away with the sodium hydroxide, it's just not quite as nice. If we go through and address mechanistically what's going to occur, well, what's going to happen? Let's draw that bond to our hydrogen. What is our base going to come in and do? What's our product? And we would have, if we want to balance this out, positively charged base, at least as drawn. What can happen now? What needs to happen?
The oxygen is going to act as a nucleophile and attack that carbon.
Our oxygen will act as a nucleophile, crunch down, kick out our bromine leaving group, and we end up with our final product. Okay, potentially in equilibrium all the way through this. Okay, we want to shift those equilibrium arrows as best we can. Okay. Next thing to address. Is there any stereochemistry to be concerned about? Okay, we've shown wedges and dashes. Is that important? So by is that important, what we would need to do, let's erase all of those, is evaluate, do we have chiral centers? Is this a chiral carbon? Oxygen, carbon, carbon, hydrogen. I for sure see a 1 with our oxygen. Call that a 4 with our hydrogen. Between carbon and carbon, is there a difference between those two? Carbon and carbon, no, but what can we do? Move one bond further away. I'm out to bromine versus hydrogen. Can I tell a difference between those? Yes, which means how many different things are attached to that blue carbon in the middle? 4, which means that is a chiral center. Do we need the wedge? Yes, it must absolutely be specified. What happens when we move to the bromine carbon, which we'll call now red? Same issue. We need that chiral center. It needs to be specified. When we shift to the product, do we have chiral centers in our product? Let's take a look at our red carbon. 1, 2, 3. Hydrogen. Our oxygen for sure. Our hydrogen lowest priority. Between our other 2 carbons, is there a difference between those? Yeah, one's connected to an oxygen, the other one's connected to hydrogen. Do we have a chiral center? Yeah, we do. We end up with 2 chiral centers. So stereochemistry is important to specify when looking at these. Okay. Is it going to matter in the course of the reaction? Okay, what do I mean by that? Well, let's go back to our starting material. And instead of drawing a dashed bromine, I make it wedged. Would we expect this reaction to work?
Yeah.
Wouldn't the oxygen interfere with the bromine being...
How did our negative oxygen come in and attack? If we take a look at how our epoxide formed, the oxygen came in from the top. What happens if the bromine was also up top? They repel each other. So if our bromine and our oxygen are on the same side of the ring, can we get that reaction to occur? No. The leaving group is on the same side that our nucleophile is coming in. Block each other, prevent the reaction from occurring, nothing happens. So when we're looking at the epoxide formation, in the case of using this as a starting material, they must be on opposite sides from each other. In the case of the ring, that's nice. We can see those with wedges and dashes. What if it wasn't on a ring? Or if it was a straight chain? When you go through and do that effectively elimination, we get a slight problem with that. We have to make sure that the oxygen nucleophile is coming in from the anti-direction of that bromine leaving group. If it does not match that alignment, the reaction won't occur. How else is that important? That's going to force the orientation of all the other groups relative to each other around the epoxide ring. So it becomes very important to watch out for that alignment. We need them opposite each other to force this to occur. Okay? For some reason I thought there was something else I wanted to say, but I can't think of it. Questions about it? Hi. Oh, that's what I was thinking of. How do you make this starting material? It's even up there for me. What kind of compound do we have here as starting material? Chandler Gilbert, you did a lot of labs with this one. What did you make? Halo hydrogen, halo for our bromine, hydrogen for effectively H2O or our OH group. How did we make the halohydrin compound? We needed an alkene as a starting material. Might as well, whoops. There's our alkene. What did we have to react with to get our alkene to generate our product? We need a source of bromine and we need a source of our oxygen. Both of those typically come in as what charge? Negative. Is that going to be a problem? What charges are, or what's reactive about our alkene? The pi, so we could look at the resonance of it, but the way our alkene is going to react first is with that negative. Okay, the electrons in that pi bond. Why is that a problem? Well, we've got 3 negatives. There's no way we can get 3 negatives to react with each other. So we have to somehow supply a positive of one of those atoms. Alkene's out. Can we get a positive oxygen? Not particularly easily. Can we get a positive bromine? What's the reagent we use?
BO2.
Br2. How does that supply our positive bromine?
It breaks, one's going to be positive, one's going to be negative.
The electron density gets close enough to that bromine to cause the bond to polarize enough that we've generated that positive bromine. Okay? And what we've done is an addition reaction, or a halohydrin formation. We put on bromine and water. Our positive atom that allowed that reaction to occur was effectively that first bromine. Okay? So we've now done 2 steps to effectively get our epoxide. So if you're looking at doing an epoxide synthesis, this is a possibility. The halohydrin is typically an intermediate, so you typically don't start with that. You usually, in the formation of an epoxide, start with the alkene. 2 steps, we now have an epoxide. Okay, so we have to go through that halohydrin intermediate to generate our final product. Okay? Yeah.
So because the Br2H2O creates the enantiomer also,
Yes.
when you do the NaH,
Yes.
sodium hydride, it's going to maintain the same stereochemistry, so you're going to go to the epoxide with only one formation, correct?
You'll have,
At
let's
least
see,
with
do
this
we get a
example,
top
because
bottom?
you can rotate it, because they'll both be back. So it'd be the
Um,
same.
Once you get the enantiomer for the product,
I think the issue with the product is that we've got meso as a product. The epoxide, I think, comes out as a meso compound, so we don't have to worry about that. The intermediate, I think, will have an enantiomer because it depends which bromine or where the bromine goes. They will always be on anti-alignment, okay? But depending on which carbon you put the bromine, you generate the enantiomer.
Right.
Yeah.
But then if you just add the NaH,
Yep.
it's automatically going to come back to this epoxide
Because it's meso. Yep. So you'll get 1 epoxide out of that. Yeah.
This is a random side.
In this case. What's
For
that?
the exam, for short answer, do you want us to draw both enantiomers, or do you want us to do this plus?
Good question. On the exam, since technically that first part has 2 possible products, there are 2 ways that you could draw out that you know that there's 2 possible products. One way, draw them both. Okay, that works. Make sure I do this right. I just flipped it, didn't I? Bromine, OH. I should have picked an easier mirror image to draw. Oh, I actually got it there. Hey, there it is. You could draw them both out. Okay, that is a perfectly valid way to do that. Why do you not want to do that?
To knowing to draw both.
It takes time, that's all I would say. So drawing both is a good option, but it takes time. So how can you get away from that? Plus an enantiomer works. You can even be more obnoxious. I'll accept plus minus. That's not technically correct, I think, in this case, but that works in this case. All I'm trying to do is identify, or you're trying to let me know that you know there's two products. As long as you specified that and it's in some format that's clear, I'll accept it. Okay? Other questions? Okay. The epoxides with our peroxy acids. So this is the MCPBA example. We've got arrows actually drawn out here. I'd intended to remove the arrows, but that didn't quite happen. Our peroxy acid generates kind of an interesting structure. So if we take a look at one way it could be written out, you might see it as it is written in the homework is RO3H. Okay, that O3 should be your trigger for looking at a peroxy, probably forming an epoxide. Okay, it's that O3 right in the middle. The reason being is that if we take a look at our structure and identify those three oxygens, to get that structure, we have to put two oxygens attached to a carbon. That's fine. But you'll notice that that last bottommost oxygen is connected to another oxygen. Why is that important? How strong is that bond in there? It's going to be really weak. Okay? Really easy to cleave because both those oxygens want their electrons. So if we put in a slight push from one direction, we can cause that bond to cleave open rather rapidly. Okay? So let's go through and start at the bottom. We'll take our alkene, and that alkene, sorry, I figured I'll erase all those, is going to take its electrons and share with our oxygen, because that oxygen's losing electrons. Okay? That other oxygen attached to it is starting to take the electrons away from it. Why would our electrons be drawn more towards the carbonyl than towards our bottommost oxygen?
More electronegative because it's attached with the other oxygen.
We'd expect it to go higher because we get an inductive effect with our other oxygen. Why else?
Wasn't the carbon more electronegative than the hydrogen?
We could go carbon being more electronegative than hydrogen as well. All of these are good answers. Can we draw a resonance structure with that pi bond? The carbon-oxygen double bond?
Yeah.
What charge builds on that carbon? Builds a positive charge. Why is that relevant? Well, we can take those electrons to stabilize that positive. Okay, so we've got a resonance argument and inductive arguments to suggest that the electrons in our oxygen-oxygen bond are going to go away from the oxygen, making it willing to accept more electrons. Okay? At that point, once we've done our electron pushing, our carbon now has how many bonds? We take a look at the purple carbon. How many bonds would it have up to this point following our red arrows? It would have too many bonds, so what do we have to do? We're going to break the weakest bond. Our weakest bond is going to be our pi bond. We can then push those electrons, depending on how we want to draw this. I think I was getting a little overzealous with this. Push them to that oxygen. Okay. The other option is instead of going directly to the oxygen, we kind of show that it pushes all the way around. Okay, why? What charge builds on that oxygen? Negative. How can we stabilize that negative? With a positive. Do we have a positive happen to be fairly close nearby? We've got that hydrogen. Why would that hydrogen be positive? What does that say about the bond between our oxygen and hydrogen? Where do the electrons spend most of their time? Why would they spend their time on the oxygen? It's more electronegative. It already lost a bunch of electron density to the rest of the structure. We can then take those electrons and complete our cycle back to our carbon. Okay? Lots of arrow pushing to go through and push that individual reaction. Okay? This is one possible way to do it. I think I've heard people doing it with radicals as well. This allows us to get an idea on what's happening with the electron flows and see how we can combine these. You'll notice all of that arrow pushing is going to make it a bit difficult to track what happened to our product. Since I don't think I provided it. Nope, I didn't. Let's go back and try and draw on what our product would look like. Let's go ahead and start up at the top. So that little black dot, what is that black dot? What atom is it? It's a carbon. What's that carbon connected to? Fair enough, that was a dumb question. We got our 3 hydrogens. What else is it connected to? To our carbon from our carbonyl. What is that carbon connected to? Where's the double bond? Why the bottom one? So what we're saying is that we are following the electron density of our arrows. We're forming the double bond from our bottom oxygen. What else can you tell me about that top oxygen? Anything it's connected to? Picked up a hydrogen. Okay. Are there any other atoms connected to this structure? No. What happened to the last oxygen? Our third oxygen. We'll go ahead and draw it relatively close, but not connected. What's connected to it?
The alkene, the former alkene.
Our former alkene. And go ahead and highlight that, I guess. Make that a red bond. So there's our red bond. What's connected to those carbons?
Another carbon.
There we go. Another carbon. We'll draw it like this for a second. And there's our CH3s, right? Is there anything that we need to be concerned about here?
Stereochemistry of that initial alkene. Would it have the
Stereochemistry. Does our structure have stereochemistry associated with it? Do we have chiral atoms? Take a look at each of those carbons. Are they chiral within our epoxide? Both of those atoms are chiral centers. If you see chiral centers pop up, you need to be aware of the potential for stereochemistry in your product. So now we've got to go back and evaluate what happened between those 2 carbons and how our bonds were formed. Okay, so let's go ahead. Let's see, can I undo that? Yeah. Let's call this our purple CH3. Call our other one our orange CH3. What is the relationship between these? What's the relationship in the starting material? Trans. They're on opposite sides. Okay. Did we draw an intermediate that would allow that trans to become cis at any given point? Okay, no. How do we know that? Well, you'd go back to the mechanism. Look when the pi bond broke. Okay, the pi bond broke with our very first arrow upwards. If we continue the electron motions around, what happens? We get an arrow that brings electrons back into the pi bond, okay, or into that pi position, locking it all in one individual step. What does that mean about the ability to rotate about the sigma bond that was forming? Can we get that rotation? No rotation. What does that mean happens in our product, the relationship between our purple and orange?
You have to stay trans.
They must stay on opposite sides of that double bond, which means if we go through and specify our orange one as dashed, our purple one needs to be wedged coming at us. Okay? So as we form our epoxides, we have to be aware that in our reaction, as the electrons shift through, okay, with our arrow drawings, we do not have rotation about our pi bond. The geometry of the substituents around the alkene stays constant. Okay? Even when we get to our epoxide product, and it looks like we don't have that double bond. Very, very important as far as evaluating overall products at the end of these epoxide reactions. Okay? Very easy question to throw on the exam. Okay? Questions about that? Yeah.
In theory, if I rotated it over, because the oxygen is looking from our plane looking at the board while it's in the plane, could I turn around and put it in the trans configuration, then put either double wedge or double dash on the oxygen?
Yes, I see what you're saying. So instead of the peroxide coming in and reacting with the top end of the pi bond, it reacts from the bottom lobes of the pi orbital?
Well, instead of doing that, come straight into it this way.
So yeah, so it's all a question of how we're viewing it. So another way we could draw out our epoxide, let's see if I can do this. I should be able to do this. Those are very terribly drawn wedges, but those are wedges. Like that. That is a valid way to draw it. Why do we typically not draw it like this? Okay, number one, yeah, it's easier to draw it the other way. The other reference is if you tried to build this structure and aim it such that that was the case, would these purple and orange bonds be in the same plane? Are they in the same plane of your paper? sp3 hybridized, they're actually aimed backwards. The only atoms that are in the same plane in this drawing would be the 2 carbons in our ring. Everything else is not in the plane of the paper, so technically everything needs to be wedged and dashed. Okay, so even with our purple and our orange, we would also have to go through and specify those as being aimed away. Just to make it more confusing, we would also have our hydrogens also being aimed away. So while that is a valid way to draw it, and it allows you to see that cis-trans alignment a little bit better with the substituents, be aware that to accurately depict it, you have to draw in all of the wedges and dashes. I'll understand what you're trying to do, but be aware of the limitations of that drawing. Okay. The other option is that you could have had it come in from the other direction. So we could have formed our epoxide. I'm going to erase that one. The other direction. Our oxygen down. Our orange would still be aimed away. And our purple would still be aimed at us. The relationship between these two, technically enantiomers, but only because specified purple and orange. If we don't have the purple and orange there, can we tell the difference between the two products? You'll end up, I think, seeing the same product. I'm a little bit sketchy with stereochemistry as well, and I have to draw and flip it, make sure. Okay? So we have 2 lobes for that peroxide to react with our p orbitals of our pi bond, either from above or below. In most cases, you generate 2 products because of that orientation. So be aware of that. If there's not a lot of symmetry in your molecule, like in this case, you might end up getting multiple products. Okay, so be aware of the dynamics of how that mechanism comes together. Questions about it? It's an interesting one. May not be the easiest, but it's interesting. Okay. So, synthesis of epoxides. We could go through and look at a couple different reactions, and we just addressed this. If we started with a cis alkene, and we did our MCPBA, remember I said our standard for our peroxide is the MCPBA. That stands for metachloroperoxybenzoic acid, I believe. So the actual structure, just in case you were curious. There's our peroxybenzoic acid. To get the metachloro, we'll talk about that nomenclature after the exam. There's our metachloro. That reagent, again, you'll notice that we have that weak oxygen-oxygen bond. We still have our reactive oxygen can push our epoxidation reaction. Okay? So you'll see the MCPBA as an abbreviation for an epoxidation. When we go through and run our reaction, we get the cis and cis products. Okay? If we have trans double bonds, we get trans products. One of the problems that we just addressed is that that MCPBA could have either reacted from the top or the bottom. And if we had particular stereochemistry associated with our starting material, even if we started with our cis, we could get slightly different products. So an epoxide formation generates two products. When we go through any individual reaction, how many products do we typically want? One. So we want to be enantioselective. We want one enantiomer to form and leave the other one behind. Okay? The epoxide reactions that we've just looked at don't solve that issue. Okay? We'll get both in both cases. So what someone went through and did is invented a new catalyst. That catalyst helped push one formation of your enantiomer over the other. So you only get one of those products. It's known as the sharpless catalyst. It's used so that we get exactly this, one enantiomer epoxide versus the other. To do that, so first off, you get your catalyst, which is the titanium oxide deal. The next issue is how we favor one enantiomer over the other. Okay? It's kind of interesting chemistry that I've never heard a reasonable explanation of. So we can either take our alkene, our titanium reagent, and then one or the other of these DET molecules. Okay? You'll notice that if you evaluate the stereochemistry through them, they are mirror images of each other. If we put in the plus conformation, the result in our product is that we get the plus enantiomer of the epoxide. If instead we wanted the minus, we would use the other reagent or the other compound, and that would generate our minus epoxide. Kind of odd chemistry. Okay, the exact mechanism is not discussed in the textbook. You're just kind of told that this is what happens, which is all I'm really going to tell you as well. If you want to favor one enantiomer or one product over another, one way to do it is you add in a completely new compound, completely irrelevant to the mechanism, that has a particular enantiomer. That enantiomer favoring, or that enantiomer presence in the solution, will cause the chemistry to occur favoring that same type. Okay? Where is this probably the most important or most relevant? If you go back to creation, where did life first start? Okay, DNA, sugars, all that have a particular handedness or rotation of light. Okay, I don't remember which one's which. Anybody know? For DNA, which way does it rotate? Is that your right hand? Goes to the right. Okay, you don't see any LDNA. Or, is it LDNA? I don't know. You don't see one of the other corkscrews of the DNA. Why? It seems very odd that if life was just started from achiral starting materials, why do we favor only one and not the other? One of the arguments behind why we favored one is it just so happened that when biomolecules were first created or started to form, they happened to be near quartz. Quartz has a handedness to it, its crystal structure. So what ends up happening is eventually you form one molecule. That molecule forces the stereochemistry on everything else, even though it doesn't actually exchange bonds. It then proliferates until you generate just one form over the other. There's all sorts of other things more complex with it than that, but it's kind of an interesting thing that happens. So a chiral center can impact chiral centers in other molecules, or forming chiral centers in other molecules without actually exchanging bonds. Kind of neat. And like I said, I've asked other people to explain that, and that's the best that I get. Oh, it just does it. Thanks. That's cool. I mean, it does just do it. Okay, so when we look at our stereoisomers, so this is what we're talking about, our above and below, we can generate the epoxides, or that forming epoxide from our top or our bottom. So we can see some slightly better versions of those drawings. Okay, which was your initial question, what you were pointing to. Okay, you'll notice they've yet again drawn them slightly differently. Each of these different angles is trying to accurately reflect what we're seeing in 3 dimensions. We try to do the best that we can when we draw them out. Okay, so different formations explain or show things slightly differently. So the main lesson out of this, the sharpless catalyst will force one formation or one product over the other. That's our big deal. Reactions of ring openings. This is probably the next most important part of this. So if we go back to our alcohols, what is necessary to break the carbon-oxygen bond? There's 2 big things that are important to break our carbon-oxygen bond in an alcohol. Holds true for our epoxides too. Oh, don't look at that. Okay, to break our carbon-oxygen bond in an alcohol, so let's draw out a quick alcohol here. What do I need to do to break the bond in between the carbon and the oxygen? One of the very first things we would refer to would be a pre-activation. We had to turn our alcohol into a good leaving group. Okay, so we could have gone through and pre-activated our alcohol to force that bond to break open. What's another option? Or what's the other thing that we need? Is that bond just going to break on its own? We need a nucleophile to come in and break it. So we've got a leaving group and a nucleophile. Those same 2 things are going to control what's happening with our epoxides. Okay? We can either go through and pre-activate our epoxide to help it break open, or, and this is kind of an added bonus with our epoxides that we didn't get with our alcohols, we can add a really strong nucleophile. That really strong nucleophile can cause that carbon-oxygen to break. So we get 2 potential conditions for this. They're both going to give you SN2 type products. We get backside attack in both cases. But depending on our conditions, we'll see our nucleophile attack at different places. Under our basic conditions, this is where I would say our SN2 in kind of quotes. And what I'm thinking of in the SN2 basic, it's not so much our backside attack, but what we're looking at is least sterics. If we're under neutral conditions, this is where I would consider something neutral to acidic conditions, I should say. This is where I would consider your SN1 type. And by SN1, I mean most stable carbocation, even though we don't form a carbocation. I will address these 2 in the next couple of slides here. There we go, fine. Okay, so, man. Oh, that's nice. Give her the answers. So if we predict the product, we want to address our stereochemistry and regiochemistry as we go through each of these. In our first condition, we've got a negative nucleophile. How do we get a negative nucleophile? Typically means the nucleophile is attached to a metal. How do we get our metal in there to be attached to a atom? Looking at basic conditions. To generate strong nucleophiles, we're almost always under basic conditions, which makes this interesting. If we're under basic conditions, do I have a good leaving group in that oxygen? We'd have to break one of these bonds. And I'm going to highlight that one because it's the bond that's breaking. If we break that open, we'd get our positive carbon and our negative oxygen. Is oxygen a good leaving group? No. Okay. Why is it okay in this case? Because our nucleophile is what's going to come in and force that bond to break. So we're trading one negative for another. Why would oxygen be a reasonable leaving group in this case? Well, the nucleophiles coming in probably aren't very stable negatives, right? Which means the oxygen would prefer to hold the electrons over our nucleophiles. And we can force our chemistry to happen, and the result is that our nucleophile comes in backside attack, Because it's a strong nucleophile, we're pushing that SN2 type characteristic, so we're going to pick the carbon of the least steric hindrance. Right? Why is that carbon least sterically hindered? What's around the other carbon? Okay, good answer to around the other carbon. More carbons. Those carbons versus the hydrogens have more electron density. They prevent that attack from coming in. Okay, and our nucleophile can bust that open. And what do we get as our product? Our oxygen. What I'm going to say as far as this goes, stereochemistry. Actually, let's not quite do that yet. There's our oxygen. Here's our nucleophile. What charge should our oxygen be? Negatively charged. Next part would be to address stereochemistry. In this case, it's not as big of a deal because, do we have any chiral centers? No chiral centers. But let's address it anyway. What's the relationship between our nucleophile and that oxygen? So to help with that, what I would do is go back to your starting material. Yep. And the way I see this is that that oxygen is a three-membered ring, and I'm going to aim that oxygen. So we do a triangle, aim the oxygen away from me. Okay, so this is now from my point of view. For you guys, be that way, right? Where does the nucleophile come in? It's got to come in from the back side. As it comes in, that bond breaks. Our oxygen is over here. The bond that just formed is that way. What's the relationship between them? Trans. They're on opposite sides of each other. That geometry has to be shown in our product in some form or another. The way, or the reason I drew it out like this is because now I can say, whoops, it's supposed to be blackened, that these bonds are still coming out at me. This bond is kind of running through the middle of it. Where's our oxygen in that case?
Still wedged, or dashed rather.
Dashed away from you. Where's the nucleophile? Wedged coming out at you. Okay? That allows me to see the geometry between those two. I could now draw that as the product and then decide after that fact, redraw it and say, do I need to specify the stereochemistry? You'll notice the oxygen is negatively charged. Does it want to be negative? Nope. Can it do anything at this point? The only thing that we've got is our epoxide and the nucleophile, which is negatively charged. Is there anything to stabilize that negative? There's not water yet. Our reaction stalls. Now we can add water to work up the reaction as a step 2. The oxide can pull our hydrogen off of water, and we can get our final product. Our alcohol and our nucleophile. Okay? What happens in the next one? So this is a point that I want to address because a few people have pointed this out. We look at the epoxide ring opening. You take a look at your product. Almost everybody goes, oh, we get a nice long chain, which means we don't get a ring anymore. Kind of, sort of. Why do we not have a ring? How many rings did we start with? 1. In the course of the epoxide reaction with our ring, we break the epoxide ring open. When we move to the next question, how many rings do we have? Could be that ring within a ring game. We've got the epoxide ring and the cyclohexane ring. What ring opens? The epoxide. What happens to the other ring? It stays the same. Nothing changes to it. All right, so when we evaluate the chemistry, look to see where your bonds are making and breaking. Only address those. If anything else doesn't change, or nothing else makes or breaks, leave it alone. So we could go through and draw the basics of our structure. Where does our nucleophile want to come in and attack? And in fact, actually, I can even add this guy in there. Our nucleophile, being a strong nucleophile, will attack the least sterically hindered position. Is that coming in from the back side, or from the back of the board, or on top of the board?
Back of the board.
Back of the board, because the epoxide is facing towards us. All right? So if we take a look at our product, we get our nucleophile being dashed away. What happens with our oxide?
Still wedged.
Still wedged. We did not touch that bond, which means we leave it the same. And we can now draw on our oxygen, which would be negatively charged initially. Nowhere within the structure to stabilize. We can now follow that up with water. And we end up with our final product. Questions about that? Okay.
If you didn't add the water, would this reaction lay more to the left in terms of equilibrium?
Depends on the nucleophile, actually. Kind of suspected that's what you were trying to ask there. I think it's going to depend on the strength of the nucleophile. I'm not going to push equilibrium reactions at you. I'm trying to decide which way it goes, okay, at least at this point. So if we're drawing it out, we're expecting it. If it goes at all, it's going all the way. Okay? What about the last case? Do we do anything to the ring?
The epoxy ring, yes,
So not the cyclohexane, so we can draw in our cyclohexane. Are we going to do anything to the carbon? We got to be super careful with this one. Now trying to figure out the rest of this. Do we have that strong nucleophile? No. So we don't have something that we can immediately have come in and attack this. So what else do we have given to us? Acid. Acid supplies what? Hydrogen. What does that hydrogen need to react with? Oxygen works. I was looking for electrons. The oxygen lone pairs will pick up a hydrogen and be positively charged. Oxygen doesn't want to be positively charged, so it starts to pull electrons. Okay? It's got three sources it can pull it from. It can go from the hydrogen, in which case we just go backwards, or these two carbon-oxygen bonds. Which of those bonds does it prefer to take the electrons from? Why the more substituted one?
because it's an overall more stable without them.
If we push this to the extreme and ignore any nucleophile presence, okay, and we just say, okay, let's see what happens if we do this. And we pull the electron density away, we get our wedge for our alcohol. What happens at that carbon? It would be what charge? Would be positively charged. If we'd done it from the other direction, our positive charge would have been on the other carbon. The other carbon is what kind of carbocation versus this one? Secondary versus tertiary. We're pulling the more stable carbocation. Okay, in the case of in the case of our acid catalyzed epoxidation opening. So what's the result? Our nucleophile, in this case, is what? The only other negative in the structure or in the solution. It's our water. Our nucleophile will come in and attack. Is it going to attack from the back side, front side?
Back.
Still backside. That bond does not break before this attack occurs. Okay? That's just not stable enough to break open on its own. So what water will do is come in from the back side just as before, our nucleophile, just like our nucleophile, and break that carbon-oxygen bond. So our oxygen should still be wedged. If we take a look, and this is, take a look at our new bond between our oxygen and our new our carbon and our oxygen. That oxygen is still positively charged. And we still have our CH3 there. We need to address the stereochemistry. What should our stereochemistry be? The oxygen came in from where? The backside of our other oxygen leaving, which means that oxygen must be dashed. Okay, why all the pause and slowness on this? What happens to the CH3 then? It ends up getting pushed to the front. We still see the inversion that we would see for an SN2. Okay, but it's happening at the most substituted carbon that we would not expect for an SN2 reaction. Okay, so our acid catalyzed mechanism is a little bit different than our base catalyzed, and it's because we now have that really good leaving group, which now changes the chemistry of those carbons. In our base catalyzed reaction, what we were looking at is the strength of the nucleophile dominating our reaction. When we look at the acid catalyzed reaction, we're looking at the strength of the leaving group contributing to the overall product. Okay? So we have to be aware of the overall reaction conditions on which one pushes which chemistry. All right, let's see. I think I got it slightly better. So here it's shown again. What we're looking at is, again, the strength of our leaving group. Under acidic conditions, the leaving group ability kind of dominates, and we favor what I would call SN1-like chemistry. Why is it not officially SN1?
Because it's still a backside attack?
It's still a backside attack. Okay? Questions on that? Looks like you're writing that down, so maybe I'll wait a little bit. But not that much longer. I'm done. Okay? Did it again. Acidic conditions generate that really good leaving group that pushes our SN1-like result. Okay, so it's important to remember when you're dealing with the epoxide ring openings. It's going to change the regiochemistry, so where our nucleophile does its substitution. Okay? Synthetic considerations. So when we're looking at our epoxides, what we're concerned about, or why they're synthetically useful, is we can elongate our overall structure, so we can bring in 2 carbons, which is kind of nice. They are carbons coming in as a positive charge, so as long as we can bring in a good nucleophile, we can add in the length of our structure. Not only that, but we do also get that alcohol functional group out of the tail end of it as well. So we get the chemistry of our alcohol in our product, while at the same time adding carbons. Okay? So it's kind of a neat little advantage. Things to watch out for. If you look at your product versus your starting materials, do kind of a head count of atoms. If you are missing 2 carbons and an oxygen, more than likely, what did you react with? An epoxide. That had to have shown up somewhere in there. Okay? The multiplication, or it's not multiplication, but the addition of that structure, making it bigger, if that difference is showing up at one of your points in your structure, you probably had an epoxide intermediate somewhere in there. So you can take advantage of looking for those counts. The other thing that's nice synthetically with our epoxides, so instead of looking at our retrosynthesis, looking at how many carbons were added into our structure, we could also use them on trying to propagate forwards. If we're trying to make a new structure, we can introduce 2 functional groups very, very close to each other. We can get the alcohol and the nucleophile chemistry only a carbon away from each other. So that can drastically change the chemistry of the alcohol It can also change the chemistry of the nucleophile because we're now introducing, again, two functional groups close to each other. And that affects our chemistry. For instance, if we take an alcohol and bring it close to a carbonyl, does that affect the chemistry of either of those functional groups? What happens to the alcohol acidity when it gets close to a carbonyl? The acidity changes so much that we, instead of calling it an alcohol, call it carboxylic acid. So by introducing two functional groups near each other, we can drastically change them and potentially allow us some more synthetic steps thereafter. Okay, so it's kind of a nice little functional group to throw in there. I will mention when it comes to spectroscopy, you have to be very careful with epoxides. So we'll address this very briefly because I think this is the last slide on epoxides. I make this a CH3. Why is it problematic? Well, let's kind of hide some of the dangers of it. If we were going to look at NMR, how many hydrogen signals would you expect to see for NMR, or this structure? Hydrogen counts, or shoot, let's try that again. NMR counts what? Numbers of hydrogens. So we could go through and say, well, how many hydrogens are in this? See, 6 hydrogens, right? Do we see a hydrogen signal or a signal in the NMR for every single hydrogen? No, if they're the same chemically, we see the same signal. Okay? It shows up in the same spot. So instead of seeing 6, okay, for sure, hopefully, you can tell me if I'm wrong, all 3 of those hydrogens should show up the same. Yeah? Yeah, so 4 might be reasonable. Okay? But what about the 2 hydrogens out here? They're attached to the same carbon, aren't they? So we might consider 3 peaks. You see 4. Why do you see 4?
Is the proximity of the one of those hydrogens to the stereochemistry closer to the oxygen, so you see a different peak?
Kind of, sort of. Not to the oxygen, though. The hydrogen that's wedged, what does it see when it looks the other direction? What does that write? It sees the other atom that was wedged, which was a CH3, right? If we take a look at our dashed hydrogen in the back, and it looks right, what does it see? Not oxygen, remember oxygen's above it. What's the bond in back? It's that hydrogen in back. Are these hydrogens, we'll call them A and B, the same? They're actually different from each other. They see different chemical environments, even though they are connected to the exact same carbon atom. Have you seen this before? Technically, yes. Alkenes. Terminal alkenes generate the same issue. The hydrogens at the end of that alkene end up showing up different because there's no rotation about the pi bond. Can we rotate about that carbon-carbon bond? Nope, because the oxygen, or that ring, prevents that rotation, which then means hydrogen A and hydrogen B end up having to be different from each other. Okay? So when you're looking at epoxide stereochemistry, which might show up in the chapter 14 homework, can't say I remember if it does or not, it will make your NMR a lot more difficult to interpret because of that additional feature. Okay? Sure, why not? Let's go ahead and end it with this. So let's take a look at a synthesis example here. So, any ideas? What do you think we're reacting with? Really? What's that? Okay, we could bring in an alkene. What section did we just end talking about? Epoxides. What functional group do you think needs to show up in our reaction? Probably seeing an epoxide somewhere. Okay. So what I personally would do I know I'm starting with this piece, so let's see if I can find where that piece is in the product. Looks like a pretty reasonable place to start. So somehow or another, I need to break that chloride bond and then make that carbon-carbon bond. So we could then go through and see how many carbons changed. Okay. Any ideas? I think I can see two possible ways to do this. That's a lie. One possible way. We just did an epoxide, so more than likely we're going to have this oxygen close up the ring. Which way is it going to close up? Should we form our epoxide to the left or to the right? Okay, well, let's draw out our possibilities. If we go left versus if we go right. Where are reactive carbons in both of these? Connected to the oxygen. So we're looking here and here, here and here. Can we eliminate one of these? Where would those reactive carbons be up in our starting material? All right, we'll call this 1, 2, 3. This would be 1, 2, and this would be 2, 3. So one of those epoxides not going to work. 2, 3, why?
The reactive carbons, number one reactive carbons takes place in
Our one position needs to be reactive. If we take a look at our product, that one position is where our chemistry is occurring. So our 2,3 epoxide cannot work in this case. Okay? So we could go ahead and erase that. Which position did our, let's make it blue so I can actually color code these a little bit better. So we said the one position reacted over our 2, which means, what does that say about our red cyclopentane ring? Does it come in as a strong nucleophile or a weak nucleophile? Okay, if it's weak, so now let's just kind of guess. We have a weak nucleophile. What does that mean? For it to be a weak nucleophile, what conditions do we want to push through? Acidic or basic? If it's weak, we want acidic so that we can facilitate that reaction actually occurring. So we would then protonate our oxygen first, and our nucleophile would attack which position?
right.
It's going to attack the right position, attack carbon number 2. It's going to go to the most substituted position because our oxygen leaving group, our leaving group now is exceptionally good, which is now going to cause that bond to break, our carbon 2 oxygen bond. Is that the one we want to break? No, we want the other one to break. We want our carbon 1 to be reactive. To get that to occur, we need to bring in something really, really strong. We would need a strong nucleophile, which means, or which is probably a bad word to use. Okay, we would push that strong nucleophile chemistry, and our ring is allowed to open in that case because our nucleophile is stronger than our oxygen acting as that negative charge. Okay? So our nucleophile needs to come in as what charge? Negative. What species is our nucleophile?
Neutral.
Red or blue?
No, red.
our red structure. Okay? And in particular, we zoom in even closer. It needs to be that carbon, right? How can we get that carbon to be nucleophilic? What charge does a nucleophile need to be? Negative. Is carbon a good nucleophile? No. How can we get carbon to be a good nucleophile? What's his name? Good call. Grignard reagent. We need electron density on the carbon. For the carbon to get electrons, it's got to get them from some source. Every atom that we've got to work with right now, except for hydrogen, has a higher electronegativity than carbon. There's no way to get electrons onto the carbon with our standard nonmetals. We have to bring in a metal. That metal is magnesium. That magnesium will insert itself into that bond. Right? Carbon is much more electronegative than the magnesium. So we could effectively call that negative and that positive. We now have the strong nucleophile. We can mix that with the epoxide and poof, our ring opens. Do we have the alcohol yet? No, why not? We don't have that hydrogen. Where do we get the hydrogen from?
Water.
We could add water, or we could even add acid. Let's see, did I actually provide the answers on that? Whoop, nope, I didn't provide the answers on that. So let's step it through. We could do our magnesium, followed by our epoxide. What are the pieces? Isopropyl, followed by H2O. I personally would probably do H3O+, but H2O should be fine. Okay. Does that make sense? Get kind of the idea on how you should break it apart? Yeah.
So I'm just very confused because you have it reversed in your review. The weak nucleophile
I was afraid
makes
of
it
that.
go to the more substituted when you're breaking it.
Yeah, the nucleophile goes to the more substituted, which would mean our nucleophile, if it's with acid, would go here.
Right, that's what I would said to start with.
Yeah, where do we want it to go? Where's this carbon in the product? We want our nucleophile to attack the least substituted.
Okay.
So it's matching that carbon up. Not the easiest thing to see with epoxides. We want our nucleophile to attack in here so that this breaks. Our nucleophile is at the least substituted position.
So it kicks it up. Okay.
So if we take a look, if we went under here, H+, that is a weak nucleophile. We're going in with a strong nucleophile because we're generating a negatively charged. Grignard reagent is a strong nucleophile with a negative. So that would then push in at the least substituted position.
Okay, I see where it is. Thank you.
Does that kind of make sense?